I'm Zhong from University of Michigan. I'm representing the thrust area number 3. As you can see, there are 5 research groups in this area. Myself in UM, Professor Posey at UM, Professor Kim Kierford at UM, and Professor Jovanovic at Penn State, who will be at UM in 2 months. And Jim and Andrea were former UM people, so I remember Al Harrow, and he's an expert on running correlation, so there is a strong correlation with UM. So the thinking process like this, so we first categorize in the gaps and challenges between the treaties and our research. I think this slide, I remember, came from probably Alice Glazer and John worked with Sarah, I guess. So I was given to present at the beginning of the talk. So in order to verify non-proliferation treaties, fissile material cutoff treaties, we identified the gaps and challenges, like to determine the mass, enrichment, and location of fissile material, and address the helium-3 soft shortage, and detect clandestine fissile material production. And that led to the research and development programs in our area called Advanced Safeguard Tools for accessible facilities. So first, Professor Posey and her students has been designing, developing, and validating the new safeguards instruments. That is helium-3 free. My timer just go off. In order to better determine the mass of plutonium samples, really, if I describe in one sentence, they have been developing fast neutron detection techniques to better determine the mass of plutonium. Professor Jovanovic at Penn State and his students has been working on a technology called laser-induced plasma spectroscopy. That's why I'm always confused by the B, not the P. So the idea is that use lasers to basically burn a thin layer of material and analyze the optical spectrum, and to see, as you can tell, if I can bring use the cursor here, you can see the different spectra from different isotopes, natural and highly enriched uranium. And the goal is in some years that they can see from tens of kilometers or few kilometers away from the satellite to see what's going on the ground, right? Professor Jim Bacek and his team at the University of Florida has been developing a metal-loaded organic liquid scintillator. Originally was designed for neutron, but they want to get additional information on gamma ray spectroscopy to simultaneously measure gamma and neutron from special nuclear materials. And Professor Kim Kierford at the University of Michigan has been working on chain of custody detectors. So if I understand it, I just have to guess. I don't know exactly where they are, but they want to make sure the materials will stay at where they are and stay where what they are, so that it is not to be substituted by something else, right? And my research at the University of Michigan is to quantitatively characterize special nuclear materials using a 3-dimensional position-sensitive CVT gamma and the neutron imaging spectrometers, right? So if I think my project will address all the gaps and challenges we have identified, determine the mass, enrichment, and helium-3 free because it's neutron detection, and what else? Oh, find the clandestine nuclear materials, right? Shipment. So now, how many minutes? Okay, fine. So just on time. So now I would like to do a quick poll. So please raise your hand if you think I did a terrible job on describing the gaps and challenges addressed by the research and development in our area. Come on. I can take it. One? Any more? How many? Oh, I love you people. You're the best on this planet. So kind of you. But I have to agree with Frank that I must have done a terrible job describing the gap and challenges. The reason, even though nobody tells me, I'm a scientist, I can learn. Last Thursday, Alex Glazer asked me to send him a slide and a number of bullet points. Say, how your research address the gaps and challenges of treaties. So I thought about it, and I had to admit to him that I really don't know. So I can't do a good job because I really don't know the gaps and challenges. So why? Because one, I don't really know exactly what has been going on, how everything has been verified and tested, and what are the shortcomings of the current technology, right? So what's happening is that, like a politician always say, he or she knows everything. Vote for me, like you saw the Republican Democratic debate. I'm the best in the world. Just vote me as your president. So a professor may tell the truth that I really don't know. I really appreciate the opportunity to talk to people yesterday at lunch about what are the gaps and challenges that in different areas. So and also someone else, I think maybe Mark or someone told us yesterday that really what is that there is no gap on existing treaties because no one would count on some uncertainties. They know 100% what they can verify. So when they made the treaty, there is no gap. So all we try to address is the gap or challenges on future treaties. That's what the best answer I could come up with from yesterday's discussion, and I think we wrote down on the slide. So really, no one knows exactly the gaps on future treaties because they have not been made yet. Okay? So I think what we should do is we use future treaty proposals as references and just use our imagination to advance technology, to make our world as safe as it could be. Okay? So then I proceed on our own research, so basically most on my imagination, how our research would fill the gaps and meet the challenges of the future treaties. So before I go into detail, I have to give you a background. You give us background on treaties and so on. I give you a background on where the technology of our research group is heading and how the CVT activities come and fit in under the bigger picture. So the core technology developed in my group is currently mostly funded by Department of Defense. We just had a kickoff meeting 2-3 weeks ago, a new 3-year program, very substantial to us, to transition from, we call the Polaris technology, to Orion technology. So to make it simple, it's like the Polaris technology is based on the analog electronics, like your analog phones you used 20 years ago, and the Orion systems use the digital electronics, like the digital cell phones and so on, like you are using today. So digital analog, who cares? What the user cares is what they can deliver. On Polaris system that people know us most, we told our sponsor that we could get 1% antigen resolution at cesium 137 keV, and we have position sensing on the sensor itself slightly below 1 millimeter, and we built imagers, and it took me 20 years, although at the beginning I thought 3-4 years, but it took me 20 years to deliver that, and we built multiple systems to deliver to DoD, and they have been tested a lot over the last several years. Now, I told sponsor that what will be new on the Orion system is that we will improve the energy resolution from 1% down to at least 0.6% at room temperature. And the position resolution will be about 3 times better than before. That will translate into higher imaging resolution. So I told them that we can make a 10 times more imaging pixels if you show image of an object, 10 times more than before. And we will increase dynamic range from 3 MeV to 9 MeV. Why? To include the neutron-induced gamma ray. Like in a weapon, if you have neutron, they will activate the explosives and the shielding, the metal, and so on. Though if we can see the structure of different things, I think you can know where we are going to, right? And in addition, these sensors can image thermal neutrons and to detect fission neutrons. So why we aim at where the magic number came to 0.6%, that or better. 2-3 years ago, I think it may not be politically sensitive, but there was a formal technical advisor from DOE came to visit our lab, and so I was quite excited to try to sell to him that we try to improve the resolution to 0.6%, and he said, oh, there is no need to get better than 1%, so there is no reason for you to get funded. I was shocked, and that was much more than when Frank told me that I didn't do a good job. That never go well with a university professor, right? So it started because I knew we can do it, and we should be able to achieve and can make an impact. But before, I had no reason because I have no access of classified information or even the experience that some of the people have in this room. Until this year, during the UITI, John Pratt of NA42 came, and when we did the measurement in DAF, and Scott Garner of Los Alamos told me that it's very important if you can tell the difference of these two lines, one from plutonium-240, one from plutonium-239, they are only separated by 3.6 keVs. They said if you could do that, that would bring a lot to our programs, right? So I heard someone give a talk about the Nobel Prize and so on. They say many things invented, people did not know what they were used for. So if you only work on things that you think is 100% useful, you will miss a lot of things. So I did not know, and for 2-3 years until this year, I learned something. So to show you the gap in the challenges so this spectrum shows this was from the Panda. I don't exactly know who made the Panda spectrum, but you can see the peaks of plutonium, so the solid and dash curve have different composition of plutonium-240 and 239. That was measured by a germanium, the best germanium detector with the resolution about 0.25 in the lab environment, right? You may not see this kind of performance in the field. So this is the spectrum we actually measured in DAF using our CVT detector with about 0.63% resolution. So I'm not quite there yet, but quite close to what the goal I told our sponsor. And you can see the peak, if you can see, I don't know whether you can see the cursor. This is the peak. Two peaks that I was talking about compared with one here and this prominent one. And you can see the germanium can see 3 peaks, but we only can see a 1 broad bump there. So you may think, oh, CVT is too bad to be useful, but Scott used his classified code using our data, and he estimated the plutonium-240 is 3.6%, and we knew the sample had 5% actual plutonium-240. So it's only within an error of 2 standard deviations. So it started to be useful, okay? If you care about why I use the 0.3% energy, so we built the first Orion prototype with this kind of performance about less than a year ago, and we have operated in DAV and a number of experiments, so it's not something I made it up, it's real, and if you come to our lab, you can see it. So it consists of 4 CVT crystals, and we did quite a careful study, compare with one of the most widely used sodium 2-inch by 2-inch sodium iodide detector, like GR135. And we think even in terms of detection, which is the most challenging thing for CVT, we can in many cases we can be better. Not saying that we will be better in isotope identification, enrichment measurement, and imaging and other things, right? So the one thing that is really unique in our group that not only we can determine what the research direction we are going, but we also influence the industry. So based on our study, our company, S3D, will launch a product, handheld instrument like I shown here, that with 4 CGTs will be launched early next year to the community. So in reality, the difference is not that bad. And this is the spectrum I just got yesterday. The bottom was from field in operation of germanium Altex detective, I think. And on the top is the CGT. And so when I passed to Claire, when I told Claire about, I showed her the spectrum, and she has a trained eye, I couldn't see. So this is the weapon grade plutonium, because from these peaks and these peaks, right? And she said, oh, I don't understand this peak in the middle. So as you can see, CGT is still worse than germanium, but basically we can see most of the peaks. But this peak we can see and germanium cannot see. That is a neutron captured by cadmium that we can sense both gamma and neutrons, and you can see we have our advantage than germanium as well. Okay, and the circle dashed circle area is what I showed you before. The difference, but if you see the germanium and CGT, the difference is not that much in the field. Okay. Another thing I think you might be interested in, this is a skyshine image on top. We recorded, not the speculated, recorded more than 200 yards away on a single crystal, not 4 crystal system. This is the 511 kV on top of a boiling water reactor. I don't want to tell the nuclear power plant name because we have done many of these. So that obviously has usefulness in safeguard and so on. Thermal neutron imaging, I see my time is running up. So the idea is that we use the combined spatial coding and time coding to do the imaging on thermal neutrons, because I showed you the peak that we can get signal even on CCT on neutrons. So the idea is that you make a mask. That mask has math behind it, although it looks like a messy, just pin the holes on it. But it has something coded in there. So when you move the mask around, there's a special time modulated curve that from a particular position. So if the neutron position changes, you get a different, I don't know whether you can tell, there's a green curve on the time coding. So the idea is that we do, because I learned the spatial coding when I was a graduate student in UK in the astrophysics community, and after I came to Michigan, I learned the time coding that started from Michigan by Les Rogers and Bernot. So this is the combination of both to do. So why we do this? So don't read the words, but on the right hand side, we did a simulation that on the top is time coding, on the bottom is spatial coding. If you have the same number of neutrons, we can do much better signal to noise ratio than just the simple spatial coding. And even with 10 times more neutrons, the spatial coding still cannot compete with our technique. But I'm an experimentalist. We haven't built the thing yet. We are building this, and the modeling works, and we will show whether it really works. But then quickly, I see the red light is on. In late April, we did some measurements in Los Alamos, and we put highly enriched uranium, depleted uranium, low enriched uranium, and on the right you can see images. Since the associate director of LANO is here, Nancy Zhou, so I have to credit the researchers, Dr. Chris Morris and Jeff Wang. They hosted our measurements. Then in May, Dr. Carter Hall at Y12 hosted our measurements. So the different colors shows the energy spectrum we measured on CVT. And you can see the two peaks I showed there, that one from uranium-235, one from uranium-238, and this is the energy window, you measure the cut rate and you measure the ratio on the bottom. So if you see, then you can see the depleted natural uranium, low enriched uranium, high enriched uranium, they are in different regions. So you can tell that we can see the difference of different samples. And on imaging, we put a RSTD sphere and through a pinhole, and so I tried to be fast. And you can see this is the recorded image, and by the maximum likelihood estimation, we estimated the radius of the sphere was 0.5 centimeter, and in reality they are 6.3 centimeters. So if you know the enrichment and you know the shape, you can estimate the mass and other things, right? Then in July, we went to DAF, and we were very appreciate the opportunity. And in this particular measurement, they put MB neutron source to activate the highly enriched uranium. So when we image of 186 keV, now you can see the HEU, and if you focus on the 60 keV from the americium, you see they locate at different places, right? And if you look at the recorded image here, the detector, and you wonder what happened, why there's a gap, that I put a question mark there, right? So you will see the next slide. So again, summarize what we have done during the first year. Successes, we have measured uranium and plutonium samples at the Llano, Y12, and DAF, and observed and estimated sample enrichment and shapes. Most of people always say how well they did and everything went well. So I'm a professor, I tell you the truth. There was something that didn't really work well perfectly. One is that during the shipment of these CVT detectors, we shipped two systems. One of the crystals just fall off. And after it came back, here it's rattled in the box, and this is the picture on the right, and you can see the crystals damaged, because our university instrument is not like the company's one, not as rugged as you would think. The shippers UPS, and they throw things on the trucks, and it causes huge damage. And also we tried to image the dry cast, the storage field in Cook nuclear power plants, but the weather was so humid during the middle of the summer, and system sparked, and it didn't work well. Again, this is the ruggedization problem not supposed to be addressed by a university group. And we learned also, when we actually measured nuclear materials, sometimes our system was overwhelmed, because especially the americium flux was so high, you want to measure enrichment at higher energies, and it's completely overwhelmed at low energy. How to deal with that, right? So back to what I started, how to identify the challenges and gaps, right? So I'm very looking forward to my trip tomorrow to IAEA Safeguards Department for the first gamma imager evaluation workshop next week in Vienna, because they will put sources there, and 4 American groups, us, Oak Ridge, and PhDs, and Berkeley, 2 CVT systems, and 2 germanium systems, and 2 British companies, and 1 French national lab. We will compete head-on to see which system will perform better in a real kind of a mock-up situation. So if you ask me what are the challenges and gaps, I tell you now, honestly I don't know, but I will learn from them. What do they need? For many years, 15 years, I said, we have the best imagers and spectrometers, and people keep telling me that, oh, that's too much, we don't need it, because it reveals too much information on weapons. But even I asked Carrie Miller, a veteran in safeguards, she doesn't know why they are interested. So I will learn and will report back next year. Thank you for your time.
But there are a number of things that come out of that expertise that are really applicable to CVT. I'll point out a few here, close to my own heart, radiation detection, nuclear